Hello everyone and welcome to the second hour of Semiconductor, which is also the last hour of this course. In this hour we are going to talk about transistors and logic gates. One question comes from both of them in your NEET examination, and that's why this hour is important. I do observe that students find transistors difficult because they do not emphasize on learning through the basics. And I have observed that when students learn logic gate, they do not emphasize on learning of Boolean algebra, which they must, because one question will come in your NEET examination from logic gates and it's easy and scoring. Now, I have said it already while dealing with wave optics. I'm saying it again here. There are two topics in physics for which NCERT is a must read. I know that NCERT becomes difficult to comprehend many a time, but for these two topics, wave optics as well as semiconductors, you must read NCERT 3 to 4 times. If you are not getting something, do not worry, mug it up right here, right now. But make sure that you have read NCERT of these two topics for sure. So without wasting time, let's start this hour where we are going to start with the topic of transistor first. So when I use the word transistor, what do we mean? A junction transistor is formed by sandwiching a thin layer of p-type semiconductor between two n-type semiconductors. A thin layer of p-type semiconductor between two n-type semiconductors. Or by sandwiching a thin layer of n-type semiconductor between two p-type semiconductor. So how do we make a transistor? You take a silicon wafer or germanium wafer, and on two sides of it, let's say you add up pentavalent impurity. If on two sides you add a pentavalent impurity, on the two sides you will get n-type semiconductor. And in the region in between them, you add up trivalent impurity. When you add up trivalent impurity, you get a p-type semiconductor. And make sure that this one which has been sandwiched between the other two should be thin in size. There should be a thin layer. When you create this type of transistor, that is called NPN transistor. To the contrary, you could have taken the same silicon or germanium wafer. On the two sides, you might have added trivalent impurities, creating p-type semiconductor, and in between them a thin layer of n-type by adding pentavalent impurity, and this will be called NPN transistor. Now we give three different names to the three regions. We call this region as emitter, this as base, and this as collector. So we have got two types of transistors, NPN and PNP. Now for every transistor we define three regions: emitter, base, collector. Emitter, base, collector. Why will the physicists choose the name emitter? Emitter is called emitter because it emits. It emits what? The charge carriers. Collector is called collector because it collects what? The charge carriers. The charge carriers are coming from where? From the emitter. Its name is emitter. So emitter emits the majority charge carriers. Collector collect the majority charge carriers. If you have got NPN transistor, then emitter will emit huge number of electrons. If you have got PNP transistor, then the emitter will emit huge number of holes. In an NPN transistor, the emitter emits huge number of electrons and collector collects them. In PNP transistor, emitter emits huge number of holes and collector collects them. So tell me, what is the direction of current inside an NPN transistor? So you will say, sir, inside an NPN transistor, yeah, emitter will emit huge number of electrons, yeah, and collector will collect these huge number of electrons. So the electron moves from left to right. If the electron moves from left to right, it means that the current has to be from right to left, from collector to emitter. If within the transistor, the current has to be from collector to emitter, outside the transistor, the current will be coming out of the emitter and entering into the collector. There is circuit representation of a transistor. When we represent the transistor on a circuit, we draw it something like this. The part which is sandwiched in the middle is the base, and the part on which current is marked, that is the emitter. If you have an NPN transistor, then current comes out of the emitter into the circuit. So that's why current is marked coming out of the emitter. Do remember, when we use the circuit representation, the one trapped in middle is the base. The one on which current is marked is the emitter, because it's the job of emitter to emit majority charge carriers. Similarly, if we think using PNP transistor, in case of PNP transistor, emitter emits, majority charge carriers, yes, and for PNP transistor, these majority charge carriers are holes. So huge number of holes move from emitter to collector. Holes are treated as positive charges. So if hole move from emitter to collector, we say that current within the transistor is from emitter to collector. So if you think of this transistor to be part of circuit, from outside the circuit, the current will be entering into the emitter and the current will be coming out of the collector. On the circuit representation, we mark the current on the emitter. That's why in case of PNP transistor, the current enters into the emitter. And you need to remember this. What? We have got two types of transistor, NPN and PNP. Each transistor can be divided into three regions: emitter, base, collector. The one which is sandwiched in middle is called base. The one which emits huge number of charge carrier is called emitter, and the one which collects the huge number of charge carriers emitted by the emitter is called collector. Now I know when I start teaching this way, students keep on thinking, but why are we learning this? Why do we need to understand that there is something called emitter, collector? All the dots will connect. Keep listening carefully. Do remember the circuit representation of PNP and NPN. How to identify the difference between PNP and NPN? In case of NPN, current comes out of the transistor and moves into the circuit. In case of PNP, current enters into the transistor through the emitter. If I draw this diagram, the circuit representation of a transistor, can you tell me this is PNP or NPN? So you will say, sir, first of all, we need to understand that this part which is sandwiched in middle is the base. The one on which current is marked is the emitter, and the third one has to be collector. Since current is coming out of the emitter and moving into the circuit, this must be which type of transistor? This must be NPN transistor, and you need to be able to identify it. Now some important points, beta. Keep focusing. These basics are important to understand transistor better. First, E is called emitter. Emitter is called emitter because it emits majority charge carriers. Do remember that emitter has to be highly doped. Emitter has to be highly doped. Why highly doped? Sir, it's emitter. It has to emit, and to emit more, it has to have more number of charge carriers. So emitter should be highly doped. Second thing, beta, emitter is kept moderate in size. Out of emitter, base and collector, you can see from the diagram, collector has the highest size, emitter has moderate size, and base is purposefully made very thin. Why? We'll explain, but to understand that, base is made very thin. Second thing, bachcho, C is called collector. Collector collects majority charge carriers which have been emitted by the emitter. The name itself, collector. Collector is moderately doped. Moderately doped. Emitter is highly doped. Highly doped. It should have huge number of charge carriers. Collector is moderately doped and large in size. So out of these three, collector has the largest size. And then comes base. Base provide interaction between emitter and collector. Do understand, we do double whammy to base. We purposefully make base feebly doped so that the base will have very less number of majority charge carriers, as well as we keep the base thin in size. So we do double whammy to base. We keep the base both feebly doped as well as thin in size. Why? The simple reason behind it is that we want the majority part of the majority charge carriers emitted by the emitter to move to the collector without interacting with the majority charge carriers of the base. If let's say in case of NPN transistor, 100 electrons are emitted by the emitter, we want that only very few of these electrons should recombine with the holes in the base. Let's say out of 100, 5 electrons should recombine with the holes in the base and majority should move to the collector. So out of 100, 95 should move to the collector. And why do we do it? I will explain this for sure, but understand that we purposefully do double whammy to the base. We keep it feebly doped as well as thin in size. When the base is feebly doped as well as thin in size, think of the case of NPN transistor. The emitter will emit huge number of electrons, but as soon as these electrons reach the base, they do not find equal number of holes there to interact with them, to occupy them. Because we purposefully keep the base feebly doped as well as thin in size. That's why these electrons keep on moving to the collector, majority of them, and only very few of the charge carriers emitted by the emitter recombine with the opposite charge carriers present at the base. Now, bacha, understand that in normal operation, for normal working of a transistor, the base emitter junction is forward biased, while the collector base junction is reverse biased. In a transistor, there are how many PN junctions? So you will say, sir, one between emitter and base. Yeah, one between base and collector. Similarly, in PNP, one between emitter and base, one between base and collector. So in one transistor, there are two PN junctions. We keep the base emitter junction forward bias and we keep the collector base junction reverse biased. This is utilized for proper working of transistor. We'll explain why and how in a little while, but all the points I have said till now will be used. So now, bacho, moving on and understanding the working of a transistor. In both transistor, emitter base junction is kept forward biased and collector base junction is kept reverse biased. Why? We'll explain. So as to make you understand, rather than explaining both PNP and NPN, we are explaining here NPN transistors. In all the electronic devices you see around you, there are transistors used. And I can say with guarantee in all of them, the type of transistor that is being used is NPN. So the question comes, a theoretical question, NPN transistors are more commonly used than PNP transistor. Why? Because in case of NPN transistor, emitter emits electrons. In case of PNP transistor, emitter emits holes. And since we know that electrons have got higher mobility compared to holes, an NPN transistor conducts better than a PNP transistor. Since an NPN transistor conducts better, they are more commonly used over PNP transistor, and that's why I am explaining the working of transistor using NPN transistor. So NPN transistors are more commonly used than PNP transistors, and the reason behind this is that NPN transistor conduct using electrons, and electrons have got higher mobility, so NPN transistor conducts better. Now, bachcho, think of this circuit. I have said that we have got NPN transistor. So the emitter is N types, the base is P types, and the collector is N types. Here in this NPN transistor, we get two PN junction, one between emitter and base and one between base and collector. For the proper working of transistor, we keep the emitter base junction forward bias. Here emitter is N, base is P. You want to keep it forward bias. So connect higher potential to base and lower potential to emitter, which is N. So higher to P, lower to N. You can see that the emitter base junction has been kept forward biased, while we keep the base collector junction reverse biased. Base is P, collector is N. Notice here, collector connected to higher, N connected to higher, and base connected to lower, P connected to lower. So you have kept the base collector junction reverse biased. Why do we do this? Beta, if the PN junction will be forward biased, we know that the current will flow given that the applied voltage is greater than the knee voltage. We have kept emitter base junction forward biased, and it's obvious, sir, emitter's job is to emit, and for emitter to emit, the PN junction connected with the emitter should be forward biased, and the applied potential should be greater than the knee voltage. Then only emitter will emit. Now the second question comes, why do we keep the base collector junction reverse biased? We don't want the collector current to be dependent on the battery connected between the base and collector. We have learned that if we have got a PN junction which is reverse biased, then under the reverse bias condition, no current flows unless breakdown takes place. When I say no current flows, it means that no current flows because of majority charge carriers. Even in reverse bias, there is a current due to minority charge carrier, but that is negligible. So we know that when a PN junction is reverse biased, there is no current till the time it undergoes breakdown, or very less current till the time it undergoes breakdown. So why do we keep emitter base junction forward bias and base collector junction reverse bias, and why do we purposefully do double whammy to the base? That is, we keep it feebly doped as well as we keep it thin in size. Now bachcho, do observe here carefully and the working of transistor will be clear. We keep the emitter base junction forward bias so that the emitter will emit huge number of majority charge carriers that has to be emitted by it. In case of N, P and transistor, since the emitter base junction is forward biased, the emitter will emit huge number of electrons. But we have done double whammy to the base. We have kept it thin as well as we have kept it feebly doped. Since we have kept the base feebly doped, there are very less number of holes available in the base region, as well as it is very thin. So once huge number of electrons has been emitted by the emitter, sir, how are you sure huge number? Because we have kept the emitter highly doped. So once emitter emit huge number of charge carriers, as these charge carrier moves from emitter to the base, on reaching the base, they find very less number of holes available to recombine. And as there are very less number of holes available in the base due to being feebly doped and thin in size, these electrons are then attracted by this positive potential connected to the collector. See here, these electrons will be attracted by this positive polarity. And if the electron moves crossing the collector into this battery this way, you will say that the current has to be in the direction opposite to it. So why do we do all these things? The simple reason, we want the collector current to be independent of VCB. To understand that, on increasing VEB, as you increase the potential difference applied between emitter and base, the current emitted by the emitter increases. As the current emitted by the emitter increases, more current reaches the collector, so IC increases. Do understand that this IC do not depend upon VCB. The potential difference between the collector and base, it does not depend upon it. Then sir, why to place here battery? No, this battery has certain role. Once the electrons have crossed the base and reached the collector, this positive plate attracts the electron towards it. So if you do not place any battery here, then definitely these electrons won't be attracted and IC will be 0. But do understand that on increasing VCB, IC won't increase appreciably. So sir, now I am able to understand few things. Which? Why is emitter highly doped? Because it has to emit, so it needs more number of charge carriers. Sir, now I have understood why the base is feebly doped as well as thin in size, because we want majority of the charge carrier emitted by the emitter to reach the collector. And you should have even understood that IC depend upon VEB and not on VCB. Though understand that you need to place a battery here, otherwise these electrons won't be attracted. But on increasing VCB, IC won't increase because the base collector junction is reverse biased. Now bachcho, understand that 5% of the emitter electron, 5% of the overall electrons coming out of the emitter combine with the holes in the base region, resulting in small base current. Remaining 95% of the electrons coming out of the emitter moves to the collector region. Technically, we should say somewhere between 1 to 5% of the emitter electron combine with the holes in the base region, resulting in a small base current, and remaining 95 to 99% of electron enters into the collector region. You should remember this. Next, bachcho, do understand that IE, emitter current, is greater than IC, because some part of the majority charge carriers emitted by the emitter also move through the base. We are saying that it's less, but it's not zero. We are saying that it's less, but it's not zero. So 5%, somewhere between 1 to 5% of the charge carriers emitted by the emitter recombine at base. So the base current comes out to be anywhere between 1 to 5% of the emitter current. So do understand that the collector current has to be less than the emitter current, because emitter current is equal to the sum of base current plus collector current. And it's obvious, who emits? Emitter. So all the majority charge carriers which are conducting current in the transistor are coming out of the emitter. So emitter must be giving out the entire current. Some part of this current moves through base, somewhere between 1 to 5%, and 95 to 99% of this current moves through the collector. The current coming out of emitter equals to current flowing through base plus the current flowing through collector. IE equals to IB plus IC. You need to remember this. This is important correlation. Next thing, bachcho, understand that you can draw rather than PNP junction like this. You can draw rather than NPN transistor like this. You can even use the circuit diagram. Remember that in an NPN transistor, the current comes out of the emitter and moves into the circuit. Second point beta that you must remember is, in a transistor circuit, the reverse bias is high as compared to forward bias. So the reverse bias potential applied between collector and base is higher compared to the forward bias potential applied between emitter and base. And there is one reason to it as well. Why? So that it may exert large attractive force on the charge carrier to enter the collector region. So you need a strong battery here, so that these charge carriers are attracted from the emitter into the collector. But do understand that increasing VCB, IC won't increase. The job of VCB is to make the current conduct through the collector. It does not change the value of IC. Now we are going to talk about the three different configurations in which a transistor is used. So a transistor can be connected in the circuit in the following three different configurations. The first one, common base. The second one, common emitter. And the third one, common collector. Now do understand, common base, common emitter and common collector comes that if the base is connected to both emitter as well as collector, it is called common base. If the emitter is connected to both base as well as collector, it is called common emitter. And if the collector is connected to both base as well as emitter, it is called common collector. So let me draw a diagram and tell me, first of all, which type of transistor it is. It is PNP or NPN. So you will say, sir, the one sandwiched in middle is base. The one on which no current is marked is collector, and the one on which current is marked is the emitter. Now, in this diagram, they have given you something like this. The connections are this way. This is tell me common base, common emitter, or common collector. So you will say, sir, here the collector is connected to both emitter as well as base. So this is common collector type of transistor. Now let me ask you one more question here, which I personally like to ask to students. Let's say this battery is of 8 volt and this battery is of 4 volt. Can you tell me emitter base junction is dash biased, forward or reverse, and base collector junction is dash biased, forward or reverse? So how to answer this particular question? It's quite easy. See here. First of all, you need to understand this is which type of transistor. This is PNP or NPN. Current comes out in case of NPN. Current enters the transistor in case of PNP. So sir, this is definitely PNP. Where the emitter is P-type, the base is N-type, and the collector is again P-type. Now sir, which junction is which biased? So for that, you need to write potential of different points. Now bachcho, let's assume that at this point the potential is 0. So here also potential will be 0. Here potential will be 4 volt. Here potential will be 4 volt. Here potential will be 4 volt. Here potential will be 4 minus 8 minus 4 volt. And here potential will be minus 4 volt. Now look at the base and emitter junction. Base emitter junction. The base, which is N, is at minus 4. And the emitter, which is P, at 0. So emitter P 0, base N-type minus 4. So base connected to lower, N-type connected to lower minus 4, and P-type connected to higher 0. This is forward bias. Now let's talk about the base collector junction. Collector is P-type connected to 4 volt, and base here is N-type connected to minus 4 volt. So N connected to lower, P connected to higher. This is also forward bias. For usual working of transistor, the base emitter junction is kept forward biased, but the base collector junction has to be kept reverse biased. So that's why this particular figure does not show a transistor under its proper working condition. Let me take one more example to understand. First of all, tell me kids, this is which type of transistor? This is PNP or NPN. So you will say, sir, the one on which current is marked, that is emitter. The one sandwiched in between is base, and the third one has to be collector. If the current enters into the transistor, it is PNP. So this is sir PN. Now if I make the drawing like this, tell me, this is common emitter, common base, or common collector? You will say, sir, you can see that base connected to emitter on the right and base connected to collector on the left. This is the type of common base. Now my next question comes. If let's say this battery is 2 volt and this battery is 4 volt. Can you tell me that base emitter junction is dash biased and base collector junction is dash biased? So you will say, sir, I need to just write potential of different points, base, emitter, and collector, and I will be able to answer. Let's assume that this point is grounded. So let's say here the potential is 0. So here the potential will be 4 volt, 4 volt, 4 volt. So the emitter, which is P-type, is at 4 volt, while the base is connected to 0. So it is at 0 volt. So N connected to 0, P connected to 4 volt. It means that P connected to higher, N connected to lower. It is forward biased. Now let's talk about base collector junction. Here you have assumed the potential to be 0. So you go here 0, 0, 0. Then you are jumping from the positive terminal of a battery to the negative terminal. So at this point, the potential will be minus 2 volt, minus 2 volt, minus 2 volt, and hence the collector will be at minus 2 volt. P collector at minus 2, N base at 0. So N at 0, P at minus 2. If you look at the base collector junction, N at 0, P at minus 2. So P connected to lower, N connected to higher. This is reverse biased. So this circuit shows a transistor within its normal working condition. The base emitter junction forward biased, the base collector junction reverse biased. So now we are going to talk about CE characteristic curves. What is the meaning of common emitter characteristic curves? First of all, common emitter means when emitter is connected both to base as well as collector. And what is the meaning of characteristic curves? Characteristic curves tells us how does the input current changes with the input potential and how does the output current changes with output potential. But the simple question comes in mind, why do teachers teaches us this? Because this is very important. It is very important to understand the concepts that I am going to explain ahead. Bachon, here what are we going to learn? We are going to learn how does IB, the input current, changes with the change in input potential. We have already learned that for the proper working of transistor, the base emitter junction should be forward biased. And for a forward biased PN junction, which type of current do you get? So sir, for a forward biased PN junction, we know that even till the time the forward applied potential is less than knee voltage, no appreciable current flows. But once the forward applied potential becomes greater than knee voltage, then the current starts to increase. So if we think of the graph of input current IB versus the input potential drop VEB, then we get the graph same as that of a PN junction in forward biased. Now to understand, let's say this first graph is plotted for the output potential VCE equals to minus 0.1 volt. So why you have written here negative sign minus 0.1? Because beta here you can see the collector is kept negative with respect to the emitter given that the transistor is PNP type. If you increase the strength of this cell to a greater extent, we get a shifted graph and the graph looks like this. So this is for higher value of VC, for higher magnitude of VC, and this is for lower magnitude of VC. Now comes the important part which I was saying. How does the output characteristic curve changes? How does the value of IC depend upon VCE? So how does the output current IC changes with the change in the strength of this battery VCE? And here comes the important part. You need to understand that the base collector junction is kept reverse bias. If I ask you, you see this current IC, why? Because sir, we have done a particular thing. We have kept the base feebly doped as well as thin in size. When the base emitter junction is forward bias, emitter emits huge number of majority charge carriers, but they are not able to recombine at base because we have kept the base feebly doped and thin in size. So they end up moving to the collector. So you see the collector current because the emitter emits huge number of charge carrier. Do understand that you do not find collector current due to this battery placed here. Then sir, why do you place the battery? Understand, this is PNP. Emitter gives out huge number of holes. These huge number of holes, which can be treated like positive charge carriers, move to the collector. To attract these holes to the battery so as to complete the current in the loop, here you have to place a battery which has got negative terminal towards the collector. For NPN, here you should have positive terminal towards the collector so as to pull the charge carriers so that the current flows in the loop. So my simple question is, will IC flow if you do not place any battery here? The answer is no. But does the value of IC depend upon the strength of this battery? Answer is no. And this is called the output characteristic curve. The output characteristic curve tells us how does IC changes, how does the collector current changes with the change in VCE. If VCE is dropped to 0, if you do not place any battery here, then these holes reaching the collector won't be attracted to the battery and the current will drop to 0. On increasing VCE from 0, the current increases and then saturates. Why saturates? Because do understand that IC do not depend upon VCE. IC depend upon how many charge carriers has been emitted by the emitter, and how many charge carriers will be emitted by the emitter will depend upon VBE. The greater the potential difference between base and emitter, the more number of charge carrier will be emitted by the emitter, and more number of charge carrier will reach the collector. So we get this type of graph. This graph tells us that you need to place a battery. If VCE tends to 0, if VCE is very small, then it has got effect on IC. But once you have placed a battery of sufficient strength which is able to pull all the charge carriers reaching the collector, then on increasing the strength of this battery, the IC won't increase, it will remain nearly constant. Now let's say you get this particular graph when the base current is 1 milliampere. If the base current is higher, it means that emitter is emitting more, so the collector will be collecting more, so your IC will come out to be higher. You get higher base current when you have got higher emitter current, and when you have got higher emitter current, you even have got higher collector current. So for higher base current, the graph looks like this, for even higher like this, for even higher like this. Now let's move on to a very interesting fact, and that is working of transistor as a switch, and this is really important. Let's say you have got this NPN transistor. You know that for the proper working of transistor, the base emitter junction should be forward biased. The base collector junction should be reverse biased. Now beta, here you can see this is NPN. Sir, how do you know? Current is coming out of the emitter into the circuit. We have already learned that IE has to be equals to IB plus IC. On increasing VBE, IE will increase, emitter will emit more. So there will be more probability of recombination taking place as the base. So when IE increases, IB increases as well as IC increases. Think of it like if IE becomes double, IB becomes nearly double as well as IC becomes nearly double. Now bachcho, we know that for the proper working of the transistor, the base collector junction should be reverse biased. If I ask you, given that we have got this particular circuit, what is the potential of emitter? So you will say, sir, emitter has been connected to ground, so the potential of emitter will be 0. If I ask you what will be the potential of base, you will say, sir, going from here 0, 0, 0, going from negative plate to positive plate, plus VEB, plus VEB, plus VEB. So the potential of the base will be VEB. Now let's talk about potential of collector. Potential of collector will be how much? So sir, here 0, here 0, here 0. You are going from negative plate of the battery to the positive plate. So 0 plus VCE. Now here look at the direction of current in the load resistance. So you can see that current IC goes up. As you move in the direction of current in the resistor, the potential decreases. So the potential of this point will be VCE minus ICRL. Now I am establishing this thing. Potential of emitter 0. Potential of base VBE. Potential of collector VCE minus ICRL. Right? For proper working of this transistor, what has to be the condition? Sir, for proper working of transistor, base emitter junction has to be forward biased, base collector junction has to be reverse biased. Now here base is P, collector is N. So if collector is N and base is P and you want them to be reverse biased, this means that the potential of the base should be less than the potential of the collector. So you can say that VBE should be less than VCE minus ICRL. Now do understand what happens as VBE is increased. If you increase the input voltage, what happens? Sir, on increasing VBE, it means that IE will increase. As IE will increase, IB will increase, IC will increase. So as you increase the input voltage, as VBE increases, you can see that VC starts to decrease as IC starts to increase. Beta, when you will increase VBE, yes, IE will increase, IB will increase, IC will increase. As IC increases, this output potential VC starts to decrease. And there will be one certain value of VBE when this condition flips, because you are doing double whammy. For this particular transistor to work properly, VBE has to be less than VCE minus ICRL, but you are increasing VBE. And because of increase in the VBE, VCE minus ICRL keeps on decreasing. So there is a particular value of VBE at which this condition flips. And once this condition flips, you say that even the base collector junction becomes forward biased and huge amount of current starts to flow in the circuit. So let's understand the input output characteristic curve to understand the working of transistor as a switch. Now first, let's understand what is the meaning of switch. A switch is something that can convert 0 into 1 and that can convert 1 into 0. The what? 0 into 1 and 1 into 0. This is NOT gate? Yes. A transistor working as a switch is as good as a transistor working as a NOT gate. In Boolean algebra, 0 means low potential, 1 means high potential. So for low input potential, you get high potential output. And for high potential input 1, you get low potential output. And this is the meaning of working of transistor as a switch or working of transistor as a NOT gate. Now do understand, if we look at the input and output potential graph, for low potential input, if potential input is very, very small, then we know that even for small forward biased, in the forward biased emitter base junction, no current flows. Till the time VBE is less than the knee voltage, no value of IE will be found. So if VBE is less than knee voltage, we know that IE will be 0. As IE will be 0, both IB as well as IC will be 0. As IC will be 0, what will be the value of output potential? So you can say that the output potential here is nothing but VCE minus ICRL. Till the time the input potential is so less that it is less than knee voltage, the output potential will be constant equals to VCE, because for the input potential less than knee voltage, IE will be 0, IB will be 0, IC will be 0. If IC will be 0, then the output potential will be same as VCE. So for low input voltage, output voltage is nearly constant and this output potential is equals to VCE. So we can say that for low value of input potential, you get high output potential. So for input being 0, the output is 1. Now, once VBE becomes more than knee voltage, then on further increase in VBE, IE increases, IC increases, IB increases. So as VBE further increases and becomes more than the knee voltage, IE increases, IB increases, IC increases, and as IC increases, we know that the output potential, which is VCE minus ICRL, will start to decrease. And this decrease is nearly linear. So do understand, as VBE increases, the emitter emits more, we get greater base current, we get greater collector current, and hence the output potential start to decrease nearly linearly. Now, there comes a point where VBE becomes so large that VC becomes so small that the base collector junction also becomes forward biased. So your base emitter junction is forward biased, your base collector junction also becomes forward biased. Under such a situation, huge amount of current flows into the transistor. IC becomes so large that the output potential nearly tends to 0. Now here we define 3 states. We say that this first region is called cutoff region. What is the meaning of cutoff region? We say that cutoff region corresponds to the region where there is no current. Since the input voltage is so small that it is less than the knee voltage, IE is 0, IB is 0, IC is 0, no current is flowing, as if wires have been cut off. So for low input voltage, you get high output voltage, okay? And this region is called cutoff region. Then come active region. Active region means the region in which a transistor is designed to work. For the proper working of a transistor, the base emitter junction should be forward biased. The base collector junction should be reverse biased. As you increase the input voltage, the input current increases, IE increases, IB increases, IC increases, and as IC increases with the increase of VEB, the output potential, which is VCE minus ICRL, decreases nearly linearly. And this region is called active region. So for active region, remember that emitter base junction is forward biased, base collector junction is reverse biased. Then comes our last region, and this is called saturation region. What is the meaning of saturation region? Once the transistor gets into saturation region, then both the emitter base junction as well as base collector junction are forward biased. Huge amount of current flows through the transistor, and we say that the transistor has reached the saturation state. When the transistor attains the saturation state, IC becomes so large because now even the base collector junction is forward biased. Then the output potential, which is VCE minus ICRL, drops to nearly zero. So how does the transistor works as a switch? The transistor works as a switch in the cutoff region and in saturation region. For low value of input voltage, you get high output voltage. And for high value of input voltage, you get low output voltage. So when the input is 0, the output is 1. And when the input is 1, the output comes out to be 0. And this is said to be transistor working as a switch. So transistor works as a switch in cutoff region and in saturation region. The transistor works as an amplifier in the active region. So now it's time to talk about working of transistor as an amplifier. So transistor working as an amplifier. First of all, we need to understand what is the meaning of amplifier. Amplification means the increase in amplitude. We know that for all three types of waves, string wave, sound wave, light wave, the intensity is directly proportional to amplitude square. So if you increase the amplitude of the wave, you end up increasing the energy associated with the wave. So a device which increases the amplitude of input signal is called an amplifier. The type of amplifier we are going to learn here is called the common emitter amplifier. Now, think that this is your input signal. The input signal is passed through an amplifier. And what does amplifier do? The amplifier increases the amplitude. So after coming out of amplifier, the time period of the wave remains the same. The frequency remains the same. It's just that the amplitude has increased. Now, bachcho, do understand the type of amplifier we are learning is common emitter amplifier. And in case of common emitter amplifier, the output and the input are out of phase. So if you send in this type of pulse, you get an amplified pulse but out of phase. So where you get crest of first one, you get the trough at output, and where you get trough at the input, you get crest at the output. Keep this in mind. For a common emitter amplified signal, the output is out of phase with the input. Now, bachcho, think of this as your common emitter amplifier. We know that if VBE, the input potential changes, so the change takes place in IE. When IE changes, IB changes as well as IC changes. And when IC changes, the output potential changes. And we know that we can write the output potential as VCE minus ICRL. When VEB changes, if a small input signal is superimposed over the input potential, then the input potential starts to fluctuate. As the input potential starts to fluctuate, IE starts to fluctuate, so IB starts to fluctuate, so IC starts to fluctuate. As IC starts to fluctuate, V starts to fluctuate. We can say that the change in potential is nothing but minus times the change in output current into the load resistance. Because understand that VCE won't change. So if for two different value of IC, you look at the change in the output potential, it is nothing but the change in output current multiplied by the load resistance. Why is the output signal out of phase with the input signal? Because as the input potential increases, the output potential decreases. That's why it is out of phase, but you can see it has got a higher amplitude. Now here we need to understand few terminologies. So important terminologies that has to be understood for an amplifier. The first thing we are going to learn is something called alpha. Alpha is nothing but the change in collector current upon the change in emitter current. The change in collector current upon the change in emitter current. So remember that the value of alpha lies between 0.95 to 0.99. We have learned that majority of the charge carriers emitted by the emitter move to the collector. So 95% to 99% of the charge carriers emitted by the emitter move to the collector. So if I ask you what fraction of the emitter current goes to collector, what is IC by IE? So you will say, sir, if IE is X, IC has to be somewhere between 95% of X to 99% of X. And when you take the value as 95% of X, 95% of the charge carrier coming out of emitter move to collector, then the value of alpha comes out to be nothing but 0.95. And when you take that 99% of the charge carrier coming out of emitter reaches the collector, then the value of alpha comes out to be 0.99. Now we need to talk about next terminology, that is called beta. Beta is also called current gain. For the common emitter configuration, the base acts like the input and the collector acts like the output. We call beta as current gain, and beta is defined as a small change in the output current, the collector current, upon the small change in the input current, the base current. So beta, we call it as well current gain, and current gain represents small change in output current, which is collector current, upon small change in base current. Now beta, if I ask you simple question, you have got this transistor, okay sir. If I tell you that 1% of the charge carriers, 1% of charge carriers emitted by emitter combine at base, recombine at base, what can you say out of it? Sir, we can say that if 1% of the charge carriers emitted by emitter recombine at base, it means that the base current is 1% of emitter current. If base current is 1% of emitter current, can you tell me collector current is how many percent of emitter current? So sir, out of the emitter current, 1% is going in base. It means that 99% of emitter current is collector current. Now can you tell me what will be the value of beta? What will be the value of current gain? That is delta IC upon delta IB, the collector current upon the base current. So sir, for this particular case, if 1% of the charge carriers recombine at base, I will say that the value of beta has to be 99% of IE, which is collector current, upon 1% of IE, that is the base current. So you get 99 by 1, which is 99. Similarly, if I tell you that 4% of charge carriers, 4% of charge carriers recombine at base, tell me alpha and beta. How will you answer? You will say, sir, it's easy. Let's say that the emitter current is IE. You are saying that 4% recombine at base. It means that IB, the base current, has to be 4% of IE. So I can say that beta has to be how much? Sir, beta is collector current upon the base current. If 4% of the charge carriers recombine at base, it means that 96% of charge carrier moves to collector. It means that 96% of the emitter current is the collector current. If you ask me what is beta, beta is nothing but IC upon IB, so that is 96% of IE upon 4% of IE, and that comes out to be 96 by 4, that comes out to be 24%. If you ask me what is alpha, alpha is nothing but IC by IE. We know that 96% of IE is IC. So IC by IE is 96%, 96 by 100, that is 0.96. And this is how easy these questions are. Do remember, since that 1 to 5% of charge carrier recombined at base, the value of beta lies between 99 to 100. If 5% of charge carrier recombine at base, it means that 95% moves to collector. So if 95% of charge carrier moves to collector, IC will be 95% of IE, while IB will be 5% of IE, and when you try to find the ratio, that ratio comes out to be 95 by 5, that is 90. If 1% of charge carrier recombine at base, it means that IC is 99% of IE and IB is 1% of IE. So when you find out IC by IB, that comes out to be 99 by 1, that comes out to be 99. So the value of alpha has to be less than 1. It ranges between 0.95 and 0.99. The value of beta has to be way greater than 1 because IC is way greater than IB. Now, bachcho, we need to talk about something called voltage gain. Voltage gain. Current gain means what? Current output upon current input. Similarly, voltage gain is nothing but voltage output upon voltage input, and that is represented by simple symbol AV. So what is voltage gain? Change in output voltage upon change in input voltage. The change in output voltage is given by delta ICRC. The change in collector current multiplied by the resistance connected to collector. The change in input voltage is delta IBRB. The change in the base current multiplied by the resistance connected to base. Now you can say this thing to be same as beta, which is current gain multiplied by resistance of the output upon resistance of the input. So you can write the voltage gain as current gain times resistance gain. I personally do not like to use the term resistance gain, but to understand that, you can think of potential equals to I into R. Yeah. So potential gain AV equals to current gain beta times resistance gain, which is nothing but the output resistance upon the input resistance. We need to talk about one more important thing here, that is called power gain. What is power gain? Nothing. Power gain is change in output power upon change in input power. We can write the change in output power as delta IC whole square into RC. We can write the change in input power as delta IB whole square into RB. So can I say that power gain equals to beta square, the current gain whole square times output resistance upon input resistance. So we can write power gain as beta square, current gain whole square times output resistance upon the input resistance. Easy thing. You know that power equals to I square R. So power gain is nothing but power output upon power input. So current output whole square into resistance output upon current input whole square into resistance input, and you can write current output upon current input whole square as the current gain whole square. Do understand that we can always write power also as current into potential. So we can always write the power gain as the power output upon power input, and that is same as current output into potential output upon current input into potential input. Current output into potential output upon current input into potential input can also be written as current gain into potential gain. So remember that power gain can also be written as current gain beta into voltage gain AV. Now talking about more important thing, that what is the relationship between alpha and beta. We know that IE equals to IB plus IC. Yes sir. If we divide each term with the collector current, we get IE upon IC equals to IB upon IC plus 1. Now bring this IE to the denominator of denominator and IB to the denominator of denominator. So you get 1 upon IC by IE equals to 1 upon IC by IB plus 1. IC by IE is nothing but alpha. So you get 1 upon alpha equals to IC by IB. The output current upon the input current is nothing but current gain beta. So you get 1 upon beta plus 1. So from here you can say, kids, that 1 upon alpha equals to 1 plus beta by beta, or alpha comes out to be beta upon 1 plus beta. So the relationship between alpha and beta can be written as alpha equals to beta upon 1 plus beta, or rearranging this, you will get beta equals to alpha upon 1 minus alpha, or you can write alpha equals to beta upon 1 plus beta. So you should be able to find the relationship between alpha and beta, and it's very easy. You just need to remember that emitter current equals to base current plus collector current. You need to remember that alpha is nothing but IC by IE and beta is nothing but IC by IP. Now we need to talk about one more important terminology, and that is called transconductance. We know that resistance equals to potential upon current, V equals to IR, resistance equals to potential upon current. Conductance is the reciprocal of resistance. Conductance equals to 1 by resistance. So if I ask you what is the definition of conductance, you will say conductance equals to current flowing upon the potential. Conductance equals to current flowing upon the potential. Here we are not talking about any ordinary conductance. We are talking about transconductance. Transconductance. So transconductance is defined as the change in output current upon the change in input voltage. And it's easy to remember. Resistance, potential upon current. Conductance, current upon potential. In whatever we have learned till now, we have always taken output upon input. So transconductance, a different type of conductance. Transconductance is change in output current upon change in input voltage. Keep this thing in mind. This is a simple thing. So now it's time to start the hero of the hour, logic gates. I personally think that they place logic gates towards the end so that people won't hate semiconductor that much, because everybody believes if the end is good, then everything is good. Logic gate is very easy to understand, and the first thing we are going to focus in logic gate is something called Boolean algebra. Now, a number system in which you have got only two digits, that is 0, which represent kind of low value, and 1, which represent high value. This is also known as binary system because you have got only two digits, 0 and 1. Now here 1 can represent many things, as well as 0 can represent many opposite things to that represented by 1. For example, if 0 represents off, then 1 represents on. If 0 represents down, then 1 represents up. If 0 represents open, then 1 represents closed. If 0 represents false, 1 represents true. If 0 represents no pulse, that is no signal coming in, then 1 represents that there is a pulse, there is a signal coming in. If 0 represents low potential, then 1 represents high potential. If 0 means no, then 1 means yes. We need to understand some basic algebraic operations done with only these two digits. The first thing we need to learn is the inverse function. We say that 1 inverse is 0 because there are only two digits. So the inverse of 1 is 0 and the inverse of 0 is 1. And the inverse is represented by a bar over the number. So remember that 1 inverse is 0 while 0 inverse gives you 1. Now here comes one basic thing. If they write 0 bar, then what will you get? So the first bar will inverse it. So you will get 1 bar, and now the second bar will inverse it again. You end up getting 0. So can I say that 0 bar is as good as 0? By the same logic, 1 bar will give you 1, and by the same logic, a bar. What is a? A variable, just like you have got x. But when in normal mathematics you take x, it can take whole lots of value. But in Boolean algebra, when you take a variable a, it can take only two values, 0 or 1. So remember that a bar is nothing but a. Now let's understand some basic addition functions. What if you need to find 1 plus 1? In your normal mathematics, 1 plus 1 is 2. But in Boolean algebra, you do not have anything apart from 0 and 1. So remember that 1 plus 1 gives you 1. What will 1 plus 0 or 0 plus 1 give you? Use your basic maths. 0 plus 1 or 1 plus 0 gives you 1. What will 0 plus 0 gives you? From your basic math, 0 plus 0 gives you 0. So the only thing which is against the normal maths is that 1 plus 1 do not give you 2 because there is no 2 in the binary system. There is only 0 and 1. So remember that 1 plus 1 gives you 1. Now, what are the outputs if we do dot? What is 1 dot 1? What is 1 multiplied by 1? From your basic maths, 1 multiplied by 1 is 1. What is 1 multiplied by 0? From basic maths, 1 multiplied by 0 is 0. What is 0 multiplied by 0? From basic maths, 0 multiplied by 0 is 0. We will learn that there is some significance of this plus and this dot, but we will talk about that later. Now let's talk about some important things, and I want you to think as I write their answer. Can you tell me what is a plus a? What is a plus a? Here you have got two variables. Your heart might be telling you to say 2a. No, that's not how it works in Boolean. If you take a as 0, 0 plus 0 gives you 0. If you take a as 1, then 1 plus 1 gives you 1. So if a is 0, the output is 0. If a is 1, the output is 1. So you can say that a plus a is nothing but a. Next, what is a plus 1? So if you take a as 0, 0 plus 1 gives you 1. If you take a as 1, then 1 plus 1 gives you 1. So in both the cases, whether you take the value of a as 0 or 1, a plus 1 comes out to be equal to 1. So you need to remember this. Next, what is a plus 0? So if you take a as 0, then 0 plus 0 gives you 0. If you take a as 1, then 1 plus 0 gives you 1. So the output has the same value as that of a. Hence, bachon, a plus 0 is nothing but a. Next one, this is important. What is a plus a bar? What is a plus inverse of a? So if I take a as 0, then a bar becomes 1. And 0 plus 1 will give you 1. And if I take a as 1, then a plus a bar, 1 plus 1 bar, 1 plus 0 will again give you 1. So whether you take the value of a as 0 or whether you take the value of a as 1, a plus a bar comes out to be equal to 1. So these are the identities you should know. Next, the same type of identities but with multiplication. Now comes question, what is a dot 1? So if I take a as 0, 0 dot 1 gives me 0. If I take a as 1, then 1 dot 1 gives me 1. So a dot 1 is nothing but a. Next, what is a dot 0? So if I take a as 0, 0 dot 0 gives you 0. If you take a as 1, 1 dot 0 gives you 0. So no matter what the value of a you take, if you take a dot 0, the answer will be 0. Next, what will be a dot a? So if you take a as 0, you get 0 dot 0, that gives you 0. If you take a as 1, then 1 dot 1, that gives you 1. So the output has the same value as a. Hence, bachon, a dot a has to be nothing but a. Next question, what is a dot a bar? So if you take a as 0, a bar is 1 and 0 dot 1 is 0. If you take a as 1, then 1 dot a bar, 1 bar will be 0 and 1 dot 0 will be 0. So irrespective of the choice of a dot a bar, a multiplied with the inverse of a gives you 0 every time. So this has to be remembered as well. Now comes my favorite, that's called De Morgan's theorem. There are two statements of De Morgan's theorem and it has to be remembered and it is useful and it is easy to remember. If you have got a plus b bar, a plus b bar is as good as a bar dot b bar. I tell students to remember it as break the rod, change the sign. So if they give you a plus b bar, it is as good as a bar dot b bar. And if they give you a dot b bar, break the rod, change the sign. So that is as good as a bar plus b bar. So these are two important formulations that are used to solve questions many a time. A plus b bar is as good as a bar dot b bar and a dot b bar is as good as a bar plus b bar. Break the rod, change the sign. Break the rod, change the sign. Okay, keep this in mind. Break the rod, change the sign. Now bachon, let's start talking about every single logic gate. The first logic gate is NOT gate. NOT gate symbol looks like this. So if the input is x and the output is y, the Boolean expression for NOT gate is that the output is nothing but inverse of input. The output is inverse of input. So if the input is 1, output is 0. If the input is 0, output is 1. That is the meaning of NOT gate. So if you think of the value of output y for different value of input, then you will say when the input is 0, the output is 1. And when the input is 1, the output is 0. This type of chart is called the truth table for this particular logic gate. Now you can think of it using an electrical circuit. If you have got this type of electrical circuit, if the key is closed, then the current will come out of the battery and will move through this parallel line and will go back into the battery, and no current will flow through the bulb and the bulb won't glow. And if you keep the key open, then the current can flow only through the bulb as the secondary line is not active. So if the key is open, the bulb will glow. If the key is closed, the bulb won't glow. This is classical example of making you understand the NOT gate. So if the key and bulb are taught, when the key is 0, the key is open, the bulb will glow. Glowing means 1. And when the key is closed, key is 1, then the bulb won't glow. There will be no light coming out, that will be 0. Electrical circuit is easy to understand. What students do not understand is the electronic circuit of NOT gate, and that's my job to make you understand. So this is what the electronic circuit of a NOT gate looks like. Now as soon as the students look at it, they're like, sir, how can you explain that this is NOT gate? This is nothing but a transistor working as a switch. When I explained the transistor working as a switch, I took an NPN transistor. I placed here a battery and one battery here, and then we grounded this emitter part, and there was one battery here. I said that for low value of input, you get high output, and for high value of input you get low output. That is the meaning of transistor working as a switch. That is the meaning of transistor working as NOT gate. But sir, these two do not look the same. They look like different diagrams. See, what they do here is they remove this much part. They do not show us this part of base connected to emitter. And they break it from here and show us two earthing. One earthing here connecting emitter to the earth, and one earthing here connecting the collector to the earth after connecting it through a resistance and a battery. So actually there has to be a battery as well as here, and understand that this is nothing but usage of transistor as a switch. Now bachcho, moving on to the next logic gate, that is OR gate. OR gate. The symbol of OR gate looks like this. There is a curved part here. For AND gate, it's flat. The Boolean expression for OR gate is that output X equals to A plus B. So if A is 0, B is 0, then X is 0. And if any one of them is 1, then the output has to be 1. If we look at the truth table for this particular gate, and we visualize different value of A, B and X, then if any one of the input will be 1, then the output will be 1. That's the basic idea of OR gate. So for 0, 0 output is 0, for 0, 1 output is 1, for 1, 0 output is 1, and for 1, 1, if you do 1 plus 1 in Boolean, you have got only 0 and 1. 1 plus 1 gives you 1. Now how can we understand OR gate using electrical circuit equivalent? So think of this as the electrical circuit equivalent. Key open means 0, key closed means 1. Now if both the keys are open, then no current can come out of the battery and flow through the bulb. So if both the keys are open, if both of them are at 0, 0, then the bulb won't glow. So for 0, 0 you get 0. But if any one of the key is closed or both of them are closed, if the first one is closed, then the current can come, move through the first key, move through the bulb and make the bulb glow. If the second key is closed, then the current can come out of the battery, move through the second key, move through the bulb and make the bulb glow. So if any one of the key is closed, then the bulb will glow. So if any of the key is kept as 1, then the bulb will glow. Otherwise, the bulb won't glow. So this is the electrical circuit equivalent of an OR gate. What does the electronic circuit equivalent of an OR gate looks like? It looks something like this. Here you have got A, B, here you have got X. Here you can see that we have placed two diodes. And the property of the diode is that current can flow from P to N but not from N to P. Current can flow from P to N but not from N to P due to majority charge carriers. Now understand here, if A and B, any one of them is maintained at high potential. Maintaining at high potential means kept 1. If any one of them is maintained at high potential, let's say A is maintained at high and we don't care about what is done with B. Then due to the high potential of A current will flow through A and then this current will go to earth. And this point X will be at higher potential. If a current I flows here, then the potential of point X will be I into R. So if any one of A or B is at high potential, then the current will flow through the resistor and this point X will be at high potential. This point X will be at low potential only when current do not flow through both of them. And for current not to flow through both of them, these both should be at low potential so that these two PN junctions are not forward biased. And when they are not forward biased, current do not flow through them. So there is no current through this resistor. So this point X is not at high potential. So only when both of them will be at low potential, this point X will be at low potential. This is the electronic circuit equivalent of an OR gate. Now let's move on and talk about our next gate, that is AND gate. The symbol used for AND gate is like this. In OR gate we got a curve and in AND gate we got a flat part. The Boolean expression for AND gate is the output X equals to A dot B. You have to do multiplication. So you say that X equals to A dot B. This is the Boolean expression. If you look at the truth table, so understand that the output will be 1 only when both the inputs are 1. So output will be 1 when both A and B will be 1. And that is the basic idea of AND gate. So if any one of the input will be 0, then the output is going to be 0. If A is 0, output is 0. If B is 0, output is 0. If both of them are 0, the output is going to be 0. That's the meaning of AND gate. So if you look at the truth table for AND gate, let's say the input are A and B and the output is X. So for 0, 0, you get 0.0, that is 0. For 0, 1, you get 0.1, that is 0. For 1, 0, you get 1.0, that is 0. But only for 1 and 1, when both the inputs are high, then only you will get the output to be high. So output will be high when the first input and the second input will be high. That's why the name AND gate. So for 1 and 1, you get 1. What is the electrical circuit equivalent of AND gate? So think of this circuit. If you keep both the keys open, then the current can't flow through the bulb and the bulb won't glow. So for 0, 0, the bulb doesn't glow, 0. If you keep one of the key closed, let's say the first one closed, then you have got 1, 0. Still, since the second key is open, current can't flow and the bulb won't glow. So for 1, 0, the output is 0. If you keep the second key closed, then for 0, 1, the first key open 0, second key closed 1, the bulb won't glow, 0. The bulb will glow only when both the keys are closed. So only for 1 and 1, the output will be 1. And this is the electrical circuit equivalent of AND gate. Now comes important part, the electronic circuit equivalent of AND gate. Now this is what the electronic circuit equivalent of AND gate looks like, and many a times students do not get it. Now here you can see from OR gate we have flipped the direction of the PN junction. Now bachon, understand that if A will be high, then this PN junction will be forward bias, reverse bias. Then sir, N connected to high, this will be reverse bias. So no current will flow through this one. If B is kept high, then this diode will be forward bias, reverse bias. Sir, N connected to high, this will be reverse bias, no current will flow. So if both of them are high, then no current flows through the diode. If one of them is low, let's say A is low and B is high, then due to B being at high potential, this second diode will be in reverse bias while the first diode will be in forward bias, so some current will flow through it. If some current will flow through this first diode, it means that some current will come out of the earth and will flow through the first diode A. If any single one out of A or B will be at low potential, then at least one of the diode will be forward biased and hence the current will flow. If the current flows in this line, then the potential of X will be low. So how can you say that the potential of X will be low? See kids, let's say this battery has got potential V and here a current flows I. You will say that the potential of X is nothing but 0 plus V minus IR. If the current flowing in this line is 0 and the current flowing in this line will be 0 only when both the diodes are reverse biased, and for both the diodes to be reverse biased, both A and B should be high. So when both A and B are at high potential, both the diodes will be reverse biased, no current flows through the resistance, and for that case the potential at X comes out to be V. And if current flows, the potential at X comes out to be V minus IR. So tell me, when is the potential at X higher? When current flows through the resistor or when the current do not flow through the resistor? So definitely the potential at X is higher when no current flows through the resistor. So the potential at X is higher. The potential at X is 1 when both A and B are at high potential, when both A and B are at 1. If any one out of A and B will be at low potential, then that diode will be forward biased and the current will flow. As the current will flow, the potential at point X will drop from V and become V minus IR. That will represent a 0 in Boolean algebra. So this is the electronic circuit equivalent of AND gate. Now let's talk about the next logic gate, that is called NOR gate. A NOR gate should be thought of an OR with a NOT. An OR with a NOT gives you a NOR, but we do not draw it this way. We have got a symbol for it. We simply draw this. We place the NOT in the front of the OR gate. So an OR with a NOT is a NOR gate. Now what is the Boolean expression for a NOR gate? So whatever output came out of the OR gate, inverse it, flip it. That is the output for NOR gate. So you will say that the Boolean expression is X equals to A plus B bar. The output of OR gate is A plus B and then inverse it. So you get A plus B bar. And we have just learned De Morgan's theorem. It says that A plus B bar is as good as A bar dot B bar. Break the rod, change the sign. So the Boolean expression for NOR gate is nothing but X equals to A plus B bar equals to A bar dot B bar. If you look at the truth table of NOR gate, the outputs will be exactly inverse that for OR gate. For an OR gate, the output will be 1 given that any one of the input is 1. If the first one is 1, output will be 1. If the second one is 1, output will be 1. If both of them are 1, then the output will be 1. So if you look at the truth table, look at the input value of A, B and the output value X. The output of NOR gate is inverse to the output of OR gate. So for an OR gate, you will get 0, 0, 0. For a NOR gate, you get 0, 0, 1. For an OR gate, you will get 0, 1 as 1. For a NOR gate, you get 0, 1 as 0. For an OR gate, you get 1, 0 as 1. For a NOR gate, you will get 1, 0 as 0. For an OR gate, you will get 1, 1 as 1. For a NOR gate, you will get 1, 1 as 0. Now let's understand the electrical circuit equivalent of a NOR gate. If I keep the first key closed, A closed, then A is 1, B is 0. Will the bulb glow? No, the current will flow through this alternate path through the key 1 and the bulb won't glow. So if any one of them is 1, if the first one is closed, first one is 1. If the second one is closed, second one is 1. If any of the key is closed, if any one of them is 1, then this bulb won't glow because the current will flow through that alternate path. The bulb will glow only when both the keys will be open. The bulb will glow only when both the keys are set at 0. So this is the electrical circuit equivalent of NOR gate. Now how do we draw the electronic circuit equivalent of NOR gate? It's easy. We have learned what is the electronic circuit equivalent of OR gate. We have learned what is the electronic circuit equivalent of NOT gate. So draw the electronic circuit equivalent of OR gate. So this much part is the electronic circuit equivalent of OR gate. And then place electronic circuit equivalent of NOT gate. This much part is the electronic circuit equivalent of NOT gate. So you can see an OR plus a NOT gives you a NOR. An OR plus a NOT gives you a NOR. So now we will talk about NAND gate. An AND with a NOT gives you NAND. And in NAND we just place a NOT at the output of the AND. So if let's say the input are A and B, the output we will get from the AND part will be nothing but A dot B. And then this NOT part will inverse it. So we will get the output as A dot B bar. So here looking for the Boolean expression, we will say that X will be nothing but A dot B bar. And from the De Morgan's theorem, we know that we can break the rod and change the sign. So we can say that A dot B bar is as good as A bar plus B bar. So sometime after solving the Boolean expression, the student get the answer as A bar plus B bar and they are not able to get this is which type of logic gate. So you should be able to get that this is nothing but NAND gate. Now bachcho, talking about the truth table. In case of AND gate, whatever output you were getting, this NOT will inverse it. So for AND gate, we know that for 0 0 we get 0, for 0 1 we get 0, for 1 0 we get 0, and only for 1 1 we get 1. So we just need to think of the inverse output. So for this time for 0 0 you will get 1. For 0 1 then you got 0, now you will get for 0 1 1. For 1 0 then you got 0, now you will get 1, and for 1 1 you will get 0. So as I said, the output of an AND gate is high only when both the input first and second is high. Now understand that for a NAND gate, the output is low only when both the inputs are high. For the output of NAND gate, the output is low only when both the inputs are high. Now bachcho, if we can think of the electrical circuit equivalent for the NAND gate, what it will look like? It will look something like this. If let's say the first key is closed, will the bulb glow? Yes, the current will come out and the bulb will glow. So for 1 0 you will get 1. For 1 0 you will get 1. If let's say only the second key is closed, so this time you have got 0. Again through this alternate path current can't go. So the current will flow through the bulb. So for 0 1 you will get 1. If both the keys are closed, the first key is closed as well as second key is closed, then you have got 1 and 1. And in such a case only, the current will choose to flow through lower resistance alternate path and no current will flow through the bulb. So only for 1 1 the output will be 0. Only for 1 1 the output will be 0. So this is the electrical circuit equivalent for NAND gate. Now let's think of the electronic circuit equivalent. It's easy. We have learned what is the electronic circuit equivalent for AND. We have learned what is the electronic circuit equivalent for NOT, and AND followed by a NOT is an AND. So an AND followed by a NOT is a NAND. Now bachcho, moving on to the next type of gate we need to learn, that is called XOR gate. XOR gate means exclusive OR gate. XOR gate means exclusive OR gate. The symbol for XOR gate looks like this. So you had this OR gate. In OR gate you place one more line parallel to this curved path. So this is called XOR gate. Now for OR gate we know that 0 0 gives you 0, 0 1 gives you 1, 1 0 gives you 1, 1 1 gives you 1. But when we are talking about XOR means exclusive OR, exclusive OR. So it means that only the first input should be high or only the second input should be high. If both of them will be high, then the output will be 0. That is the meaning of exclusively OR gate. So only the signal from first input or the second input should be high. So the Boolean expression for XOR gate looks like x equals to a dot b bar plus a bar dot b. Now this is something symmetric and you need to remember it. For XOR gate, the Boolean expression is a dot b bar plus a bar dot b. And if you visualize the truth table, let's say the two inputs are a, b and the output is x. Think for the first case, a being 0, b being 0. What will be the value of x? So you have got a dot b bar. So 0 dot 0 bar 1 plus a bar dot b. 0 bar, that is 1 dot b, 0. So what you get is 0 plus 0, that gives you 0. So 0 0 gives you 0. What if the input are 0 and 1? So the output of exclusively OR says that for 0 1 you will get 1. How? Let's see. A is 0 and b is 1. So here you will write 0 dot 1 bar plus 0 bar dot 1. Now 0 dot 1 bar gives you 0 dot 0 plus 0 bar gives you 1 dot 1. 0 dot 0 becomes 0 and 1 dot 1 becomes 1. So the output comes out to be 1. Hence 0 and 1 gives you an output of 1. From symmetry, 1 and 0 will also give you output of 1. Now let's talk about 1 and 1. If both the inputs are high, then the output will be low. For 1 1 you get 0. So think of it, x equals to a is 1 and b is 1. So 1 dot 1 bar plus 1 bar dot 1. 1 bar is 0. So you get 1 dot 0 plus 0 dot 1, that is 0 plus 0, that is 0. So notice that if both the inputs are high, the output is low. So what is the meaning of XOR? Exclusively OR. For OR gate, even for 1 1 you get 1. For exclusively OR gate, it should be exclusively OR. Only one of them should be high. Either the first one should be high or the second one should be high. Now this is what one of the electronic circuit looks like whose output is same as that of XOR gate. How to explain? See. Here you can see that the first input is named as A, the second input named as B. This signal goes through A here and A here. After crossing this NOT gate, this becomes A bar. And this same signal A goes here. And the signal B comes from here, B and B. After crossing this NOT gate, the output of this NOT gate becomes B bar. And this same B goes into this upper AND gate. The output of AND gate is nothing but AND gate simply multiplies. So from here you will get A bar dot B. From here the output will be A dot B bar. And then these two are the input of the next OR gate. What does the OR gate do? Simply add them up. So you can say that Y will be nothing but A bar dot B plus A dot B bar, which is nothing but the Boolean expression for a XOR gate. So this whole arrangement represents a XOR gate. Now let's move on to the next gate, and that is called the exclusive NOR, XNOR gate. Now what will exclusive NOR do? Simply take the output of XOR and inverse it. That is the output of exclusive NOR. Think of it, a XOR plus a NOT gives you exclusive NOR. So this is a XOR, this is a NOT. Replace both of them and simply place a NOT in the front of the XOR. Now the Boolean expression for this goes like Y equals to A bar dot B bar plus A dot B. And you need to remember it, A bar dot B bar plus A dot B. So this is the Boolean expression for an exclusive NOR gate. If you look at the truth table, simply think of the truth table of XOR gate and inverse it. That's the truth table for exclusive NOR gate. Okay. So now we will talk about something called universal logic gates. Remember that NAND gate and NOR gate are universal logic gates. Just by repetitive usage of NAND gate, I can create all the other type of logic gates. And just by repetitive use of NOR gate, just using NOR gate and NOR gate and NOR gate again, I can create all other type of logic gates. So NAND gate and NOR gate are universal logic gates. Remember that all other logic gates can be formed from them just by using any one of them repetitively. So the first thing we need to learn is how to create NOT gate. Now understand that NOT gate is little bit different from all the other logic gates. All the other logic gates we learned, OR, NOR, XOR and NAND, all of them were 2 input and 1 output. But our NOT gate is only 1 input and 1 output. So question comes, how do you make a NOT gate using a NOR gate? So as to make a NOT gate from a NOR gate, what you need to do is simply fuse the 2 inputs of the NOR gate. When you join the 2 inputs of the NOR gate, you get only single input and single output. And hence you convert a NOR gate into a NOT gate. So just by fusing the 2 inputs of the NOR gate, you convert a NOR gate into a NOT gate. And that's how you make a NOT from NOR. So prove it. It's easy. If here the input is A, here you will get A, here you will get A. What does OR do? OR add it up. And what does the NOT do? Then sir, NOT take its inverse. So can I say that X has to be nothing but A plus A bar? And if I know that X has to be A plus A bar, and I know that A plus A is nothing but A, so can I say that X is nothing but A bar? So the input is A and the output X is A bar. It means that the output is inverse of input. Hence, this NOR gate has been converted into a NOT gate. Similarly, how to create NOT gate using NAND gates are the same problem. NAND has got 2 input, 1 output, while NOT has got 1 input, 1 output. So how to convert a NAND gate into a NOT gate? Sir, just join the 2 inputs. So if you fuse the 2 inputs of the NAND gate, it converts into a NOT gate. And this is how create a NOT from NAND. You will say that if the input is A, here you will get A, here you will get A. The output of this NAND gate will be nothing but A dot A bar. So we can say that X is nothing but A dot A bar. And we know that A dot A will be nothing but A. So X will be nothing but A bar. So this is how you get NOT from NOR and NAND. And it's easy to remember. Just fuse the input of either NOR or just fuse the input of NAND. It converts into a NOT. Now understanding how to construct an AND gate from NAND gate. How to construct an AND gate from NAND gate. Bachcho, an AND plus a NOT becomes a NAND. And a NAND, this whole part is NAND, plus a NOT. This whole thing will be nothing but AND. As I said that A bar bar is A. If you place 2 NOT gates, they cancel out each other's inverse function. So if you take a NAND gate, which is nothing but an AND with a NOT, and then you place one more NOT gate. Sir, this is not NOT gate, this is NAND gate. No beta, this is NOT gate. If you fuse the input of the NAND gate, it becomes a NOT gate. So an AND with a NOT is nothing but an AND gate. So beta, using 2 NAND gates, you can make an AND gate. Using 2 NAND gates, you can make an AND gate. Similarly, using 2 NOR gates, you can make an OR gate. You take an OR gate and taking the output of NOR gate, if you place one more NOR gate by fusing its 2 input, here you have got an OR with a NOT with a NOT. An OR with a NOT is nothing but OR. Inverse it twice, it becomes the same. So similarly, 2 NOR gates can be used to form an OR gate. Keep it in mind. Next, bachcho. How to construct OR gate by using NAND gate repetitively. So understand that 3 NAND gates 3 NAND gates has to be used to make an OR gate, and the structure looks something like this. So use one NAND gate, second NAND gate, third NAND gate, and these 3 NAND gates give the output same as that of an OR gate. So how can you say? See, let's say the input to first one is A. So the output here will be A dot A bar, and A dot A bar is nothing but A bar. If the input to second one is B, here the input will be B, here the input will be B, and here the output will be B dot B bar, that is same as B bar. And then this A bar and B bar goes into the third NAND gate. So you can say that Y equals to nothing but A bar dot B bar and then not. So NAND. So A bar dot B bar bar. Now use the De Morgan's theorem. Break the rod, change the sign. So you'll say that Y equals to A bar bar plus B bar bar, and beta A bar bar is nothing but A, B bar bar is nothing but B. So you can say that Y equals to A plus B. Hence the output is nothing but the sum of A and B. This means that this whole combination of 3 NAND gate gives you nothing but an OR gate. Similarly, beta understand that using 3 NOR gates in the same fashion, replace this with a NOR gate, replace this with a NOR gate, replace this with a NOR gate, the output will give you AND gate. Remember that. Similarly, 3 NOR gates can be used to form AND gate. If they ask you in question, how many NAND gates will be required to form a NOR gate? So you know that to form an OR gate from NAND gate, you require 3 NAND gate. If you want a NOR gate from NAND gate, place one more NAND gate here as a NOT. So here you have got an OR plus a NOT will give you NOR. So how many NAND gate required to make an OR gate? 3. How many NAND gate required to make a NOR gate? I will have to use one more. And that's why you will have to use 4 NAND gate to make a NOR gate. So that's all in this hour. See you guys.